I believe we are live. Thank you so much for waiting. I was taking another class. थोड़ा सा late हो जाता when you have back-to-back classes. Anyway, thank you so much for joining this class. Thank you so much for waiting. And in today's class, we are going to revise the chapter of chemical equilibrium. If you're wondering about ionic equilibrium, do not worry. We will take a different revision lecture for ionic equilibrium, which will be in the month of June, probably in the beginning of June, so don't worry. Today we are going to discuss about chemical equilibrium chapter. This forms the basics of all the equilibrium, yes, of all the different types of equilibria, and this is going to be a quick revision session, so please pay a lot of attention, please focus. Let's get into it. So my dear friends, in case you are new to the channel, welcome to Catalysis by Vedantu. My name is Pahul and I am an alumnus of IIT Bombay. I have lots of hobbies, as you can see on the screen, but I'm not able to do biking and traveling because of the lockdown. Anyway, so are you guys ready to revise chemical equilibrium? It's a very small, very easy chapter, so it's going to be a very quick revision. Once the revision is done, we will chat with each other. Fine, let's get into it. So my dear friends, what is an equilibrium? Equilibrium is a condition in which things are stable in nature, yes? Whenever I think of equilibrium, I think of something like this. I think of something like this, where you have a tiny little ball which is, sort of rotating around in this particular bowl. And what happens is, it will move around here and there, and ultimately settle at the bottom. Yeah. So this is what comes to my mind whenever I think of an equilibrium, and this is what you also should think of. Now, talking about equilibrium in terms of a chemical reaction. Okay. In a chemical reaction, you have your reactants going towards the products. And since this is a reversible reaction, the products are also going back towards the reactants. So what's happening over here is, in case of a chemical equilibrium, you will have a dynamic equilibrium. Do you remember that? What is a dynamic equilibrium? Reactants are converting into products and products are also getting converted into the reactants at the same time, but the overall concentrations are the same. Okay, so let's say you have 10 moles of the reactants and 5 moles of the products at the equilibrium. This could be the equilibrium, yes. Let's say one of these moles, okay, one of these moles gets converted to the product. What will be happening at the same time is one of the moles of the products will be converting into the reactants. This thing is going on, but the overall concentration of the reactants and products does not change. This is a dynamic equilibrium. One more very simple example of a dynamic equilibrium could be this kind of a system where there is a hole in the bucket. Okay, imagine that that's a bucket. There is a hole in the bucket. There is water inside the bucket. The water is flowing out of the bucket. Okay, but there is a tap on top of the bucket which is filling in water at the same time. Do you realize that if the rate of incoming water is equal to the rate of outgoing water, the level of water will not change? Level is constant. Even though water is coming in, water is going out, but the level of water is constant. This type of an equilibrium is known as a dynamic equilibrium. So in reactants and products, the same thing is happening, and in that dynamic equilibrium, one condition that we have to remember is that rate of forward reaction is equal to the rate of backward reaction, isn't it? Rate of forward reaction equal to rate of backward reaction. This is the condition for chemical equilibrium. Everyone knows that. All right. Now moving into an actual chemical reaction. So the reaction that I'll take for simple purposes is this reaction which I always take. It is not really a chemistry reaction. I take one slice of cheese plus 2 slices of bread gives me 1 sandwich. Whenever I teach reactions, this is what I take for an example. Okay, let's say this is the reaction. Okay, and let's say you have 10 slices of cheese, you have 20 slices of bread, whatever, okay, so on and so forth initially. After some time, at time equal to t1, if I have used 2 cheese slices, people, can you tell me how many bread slices have we used? अगर 2 cheese slice use कर लिया, so how many bread slices have we used? Do you realize we have used 4 bread slices over here? And how many sandwiches have we created? We have created 2 sandwiches. at t equal to 1. If this is the case, now my dear friends, notice I will write something and then try to fill in these values and tell me whether that's correct or not. Okay, I can write minus 1 by 1 times delta cheese is equal to minus 1 by 2 times delta of bread. It is equal to plus 1 by 1 times delta of sandwich. Can I write this? My handwriting might not be the best, but I'm pretty sure you are smart enough to understand what I'm writing. Yeah. What is the change in cheese over here? Delta cheese is 2, delta bread is 4, delta sandwich is 2. But do you realize that since cheese is decreasing, I will have to write minus 2. Since bread is decreasing, I will have to write minus 4. Yeah. So since cheese is decreasing, delta cheese is minus 2. Minus 2 into minus 1 is 2. Minus 4 into minus 1 by 2 is 2. How many sandwiches are created? Plus 2. Plus 2 into plus 1 is also equal to 2. So I'm pretty sure you understand this logic exists. For a general reaction now, I'll write it in a better handwriting. What you can write is minus 1 by A dA by dt. Okay, where small a is the stoichiometric coefficient, capital A is the change in the reactant. This could be the change in the concentration of reactants, change in the mole of reactants. Chalega. Okay, this is equal to minus 1 by B dB by dt. This is equal to plus 1 by C dC by dt, which is equal to plus 1 by small d d of capital D by dt. Right? I hope you remember this idea. Yes. I hope you remember this idea, and I'm pretty sure you've dealt with this idea in chemical kinetics as well. Okay? So this is a very important idea for chemical equilibrium. Sometimes questions are asked according to this. Fine. Now let us move on into the law of mass action. What does law of mass action say? Law of mass action says that let's say you have a reaction like this, A times A plus B times B is going towards products. We don't care about what the products are right now. Law of mass action is an empirical law. Empirical means it was determined experimentally sometime in the late 1800s. Okay, and this law essentially tells us that the rate of the reaction is equal to some constant K. Okay, some constant K times active mass of A to the power A into active mass of B to the power B. What is this active mass? Active mass is essentially the part of the system participating in the reaction. Okay, so over here what's happening is that A molecules of A are reacting with B molecules of B. So essentially you could write them as A into A, so on and so forth till you reach small a, B into B into B into B till you reach small b. So overall this law can be written as K into A to the power A into B to the power B. Now these active masses could be concentrations, which is the most common way. These active masses could be partial pressures, which we will see in some time. Yeah. So this is equal to rate, everyone knows that. And my dear friends, in case you have AA plus BB going to C times C plus D times D, can you write the rate of forward reaction and the rate of backward reaction? What is the rate of forward reaction? Rate of forward reaction is equal to K into, I'll write KF for K forward, A to the power A, B to the power B. K backward can be written as C to the power C into D to the power D. So my dear friends, for the equilibrium, K forward is equal to K backward. Rate of forward is equal to rate of backward. Yeah. So my dear friends, in case you equilibrate these two ideas, okay, for equilibrium constant Kc, what you will do is rate of forward reaction is equal to rate of backward reaction. So Kf into AA into BB is equal to K backward into Cc into D to the power D. So what does this give me, people? You get K forward by K backward is equal to the equilibrium constant Kc. C means equilibrium constant in terms of concentration, and this is equal to C to the power C D to the power D upon A to the power A into B to the power B. Very simple, very obvious. Yeah, so simple that we were able to derive this idea in the revision class itself. Equilibrium constant Kc, which is equal to K forward by K backward, which is this. Now, my dear friends, do you realize that this condition is applicable only at the equilibrium? This condition is applicable only at the equilibrium, but you could do this calculation outside of the equilibrium as well, right? In the chemical laboratory, when you start a reaction, you can make the measurements of concentrations and come up with this, the thing that I'm circling in black. Only at equilibrium is this black circled thing equal to Kc. सिर्फ और सिर्फ इक्विलिब्रियम पे ये जो है वो इक्विलिब्रियम कांस्टेंट कहा जाएगा. एट अदर कॉन्सेंट्रेशंस अपार्ट फ्रॉम द इक्विलिब्रियम, लेट्स से जस्ट स्टार्टेड द रिएक्शन एंड मेजर्ड द कॉन्सेंट्रेशंस, then my dear friends, in any other general condition, this black thing is known as the reaction quotient. Okay, so reaction quotient is also the same thing. I'll write it. Writing this is the toughest thing about this chapter. B to the power B. Okay, and this is known as the reaction quotient, and these are applicable at any point of time other than the equilibrium. ठीक है जी, तो यहाँ मैं I'll write this idea in blue color as well, that this is applicable at any point of time, not just the equilibrium. Okay, so now my dear friends, do you remember I told you about this system of the ball? Okay, let's try to write down the relationship between reaction quotient and K equilibrium. What you need to do in order for yourself to remember. Okay, some people get confused in this idea. I'll tell you how to remember. Okay, think of this ball. Okay, think of this ball as the reaction quotient, and think of this entire thing as the reaction. This entire system is the reaction. Okay, now my dear friends, this middle line that we have, okay, this middle point that we have, this is the point of K equilibrium. Let's say Kc. Now my dear friends, if Q is greater than K equilibrium, if Q is greater than K equilibrium, which is the example that we've given over here, the ball will move back. If my Q is ahead of the K equilibrium, my ball will move back. So in this case, the reaction moves backwards. Realize this? Q greater than K equilibrium, reaction moves back. Similarly, Q less than K equilibrium, just imagine this system in your brain. Q is less than K equilibrium, it will move forward. As simple as that. It will move forward. Yeah, this imagination helps now. So Q less than K equilibrium, reaction moves forward. As simple as that. Alright, and finally, if Q is equal to K equilibrium, then we call it the equilibrium. As simple as that. Okay, so equilibrium constant, reaction quotient, equilibrium is attained. The system always wants to attain equilibrium. Very, very simple. Now my dear friends, there is another equilibrium constant called Kp, and this is generally used for gaseous reactions. You can also use it for liquid reactions where there are partial pressures. Okay, so generally for gaseous reactions. So let's say you have a gaseous reaction, you have H2 plus N2 giving you NH3. लिख सकता हूं मैं? Fine. This is a reaction that I can write. So over here, do you realize that instead of talking about concentrations, it's easier to talk about partial pressures of these gases, because H2, N2 and ammonia, all of them are gases. ठीक है? So since these are gases, I can write Kp to be equal to the partial pressure, okay, the partial pressure of NH3 raised to the power 2 upon the partial pressure of hydrogen raised to the power 3 into the partial pressure of nitrogen raised to the power 1. This is known as Kp. Is just a different way of writing the equilibrium constant, talking about partial pressures rather than concentrations. If there is a system in which you can have both Kp and Kc, for example, over here you could write concentration as well, isn't it? Moles per liter, that is concentration. So moles of hydrogen per volume of this entire mixture, it can give you a concentration of hydrogen. So the relationship between Kp and Kc is this. Kp is equal to Kc into RT to the power delta N. What are our assumptions over here? The assumptions over here are that we are assuming ideal gas behavior. Okay, this is an implicit assumption whenever we convert Kp into Kc, that we are following an ideal gas behavior. Okay, ठीक है. So what is delta N? Delta N is the number of moles of products minus number of mole of reactants. Fine. So over here, can you tell me what is delta N in this particular reaction? What is delta N? Delta N is equal to 2 minus 3 plus 1, that is 4, that is equal to minus 2. Total number of moles of gas are decreasing in this reaction. So this is the idea that will be applicable. Kp is equal to Kc into R2 to the power delta N. Fine. चलो ये तो बहुत simple हो गया. Now let us talk about homogeneous versus heterogeneous equilibrium. Homogeneous equilibrium is simple. Yeah, homogeneous equilibrium is A plus B going to C plus D, and all of these are, let's say, liquids. All of these are, let's say, aqueous. All of these are, let's say, gases. This is a homogeneous equilibrium, and over here it's very simple to write the law. It's very simple to write the K equilibrium. But heterogeneous equilibrium mein you can have solids and liquids and gases, all of them. So your reaction will look something like this, where AA plus BB is going towards, let's make an equilibrium reaction, C times C plus D times D. And let's say over here A is a solid, B is gaseous, C is gaseous, D is gaseous. So in this particular case, the Kc that you will write, okay, includes only the most volatile phase. Okay, in case C was a liquid over here, okay, chalo maan lo, this is a very rare case, no one is going to ask you this, but in case C was a liquid, A is a solid, then you will include only the most volatile phases. What is the most volatile phase over here? What is the most random phase over here? Gaseous phase. So the equilibrium constant will be written only in the terms of gases. Okay, D to the power D upon B to the power small b. If C over here was gaseous, yeah, then you will include that into your rate law as well. As simple as that. So you just have to ignore the less volatile phases, because think about it, solid, gas, gas. Now all the difference that is happening inside the volume of the reaction mixture will be because of the gas, right? Solid volume will hardly change compared to the gaseous volume. So the mass action that is happening, the active masses that are changing will be a lot more drastic for gases. Concentration of the gases will change a lot. Concentration of the solid negligible compared to the gases. Fine. So in heterogeneous equilibrium, only take the most volatile phase. Very nice. बड़ी simple सी बात थी. चलो आगे बढ़ते हैं. Then do you remember what is degree of dissociation? Degree of dissociation is alpha. How do we do the calculation? I have taken a reaction over here for you guys for me to be able to explain it. कैसे करेंगे इसको? PCl5. Let's say initially you have capital A amount of this, 0 of this, 0 of this. At time t1, what we can write is A minus A alpha is reducing. What is this alpha now? This alpha is basically the fraction of the initial amount. Okay, this is the fraction of the initial amount that has already reacted. Fine. This alpha is the fraction of the initial amount that has reacted. Let's say, I say you had 20 apples, I took away 5% of the apples, something like that. Okay, to take a very easy example, let's say you have 100 apples, I take away 5% of apples. How many apples do you have now? You can do the calculation. Yeah, you have 100 minus 5, 95 apples. Very simple. Yeah, so that 5% is exactly what is alpha. the fraction or the percentage of the initial amount taken away. ठीक है जी, तो यहां पे I can write it as A into 1 minus alpha. PCl3 will simply become, कितना बन जाएगा ये? Reduction over here is A alpha, so this also becomes A alpha, this also becomes A alpha. Is that fine? ठीक है, got it? All right. Nothing too complicated about it. So degree of dissociation, I'll write over here once again, is just the fraction of initial amount reacted. As simple as that. यहाँ पे at time t1 this will be A into 1 minus alpha, this will be A alpha, this will be A alpha. Okay, if it had a stoichiometric coefficient, let's say C, then you will have C times A alpha over here. As simple as that. ठीक है, बढ़िया, कोई मुश्किल बात नहीं है इसमें. It's a very simple idea. Degree of dissociation is the fraction of the initial amount that gets reacted. Very simple. Now let's move on into relationship of K equilibrium and dG. dG is essentially delta G. dG, delta G, same thing. Okay. So delta G of a reaction is equal to delta G naught. What is the difference between delta G and delta G naught? Delta G naught is at standard conditions. This is a standard. Okay. ठीक है, this is a standard. So over here you have 1 mole of all constituents. Okay, 1 mole of all constituents, 1 molar concentration, 1 molarity. Okay, so reactants and products all are 1 molar to define delta G naught. Okay, your pressure is equal to 1 bar, your temperature is equal to 25 degrees Celsius. So delta G naught is delta G at standard conditions. How are they related to each other? Delta G is equal to delta G naught plus RT ln Q. Okay, great. Now all of us know that at equilibrium, delta G is equal to 0. What is delta G? What is delta G? Delta G is change in Gibbs free energy. What is Gibbs free energy? Gibbs free energy is the energy contained inside the system which it can use to do the reaction. That is why when delta G decreases, it means that the system has used its own energy to do the reaction. And once that happens, once it has used all energy, the reaction will stop happening. Which means that all the energy has been used now, delta G is 0. Equilibrium aa chuka hai. When you are at equilibrium, the system is not using any more energy of its own to do the reaction. Yeah. Delta G, Gibbs free energy, is the amount of non-expansion work that the system is capable of doing. Something that is an idea of thermodynamics. So over here at equilibrium, since the system is not doing any more work, the change in its own Gibbs free energy is 0. So delta G is 0, but delta G naught is defined only at standard conditions, right? So if we put this guy equal to 0, we can get an expression between delta G naught and minus RT ln K equilibrium. Why K equilibrium? Because reaction quotient will turn into K equilibrium at equilibrium. Yeah. So you can write over here dG is equal to minus RT ln Kc. ठीक है, fine, great. Then the other equation that I have given to you over here, of course this is a revision class, we won't be doing derivations. This is the Van't Hoff equation. I am pretty sure some of you have recognized this already. Yeah, ठीक है. This is the Van't Hoff equation. What this does is it gives you a relationship between the equilibrium constants at different temperatures. Looking at just the enthalpy of the reaction, this can tell you what is the difference between the K equilibrium at different temperatures. Do you remember that when you change temperature, K equilibrium changes? This is what the equation is quantifying. Okay, K equilibrium will not change unless you change temperature. If you change concentration, pressure, volume, whatsoever, K equilibrium will remain constant. But if temperature changes, then your K equilibrium's value changes, and those values are related to each other by the Van't Hoff equation. Please remember this equation. This is important. We will use it in some question tomorrow when we are doing the question solving of this particular chapter at 8 p.m. And now, my dear friends, finally, let's talk about Le Chatelier's principle. His actual pronunciation will be a very weird Le Chatelien, something like that. French pronunciation, I'm not sure. Let's call him Le Chatelier for Ease of use. Le Chatelier's principle tells us how if we change different reaction conditions, reaction will go forward or backward, so on and so forth. Yeah, fine. So let's do this with the help of an example. Let's make it a little more fun. State the effect of the following in the above equilibrium reaction. Over here, what are the facts of the reaction? Let's try to understand the facts of the reaction first of all. Okay. Delta H greater than 0. This means that this is an endothermic or exothermic reaction. This is an endothermic reaction because delta H is greater than 0. It needs heat. If delta H was less than 0, it was releasing heat. Over here, what is the delta N gaseous? Delta N gaseous is 2 minus 2. That is 0. Yes. Now people, let us revise all of these points and also see what will happen in the case of this particular reaction. What is the effect of increased temperature? What is the effect of increased temperature? Increasing temperature implies that you go towards higher energy. Since this is an endothermic reaction, do you realize that the reactants are at smaller energy than the products? The products are at higher energy. So you increase temperature, you have to go towards higher energy. So over here in this reaction, you go forward. Yeah, you go forward. What if you decrease pressure? Acha. If you decrease pressure, you can assume, okay, if you decrease pressure, you can assume that is an increase in the volume. If you increase the volume, it has to go towards more number of gaseous moles. Yeah. If you decrease pressure, you can imagine that the volume is increasing. That is how you imagine. If it's a constant volume system, then no change will happen. If volume increases, the system goes towards more number of gaseous moles. If the volume decreases, the system goes towards less number of gaseous moles. Over here in the reaction, there is no change in the number of gaseous moles. So this particular reaction has no change by the change in pressure or volume. Always remember, volume change dictates the change. If you have an isochoric vessel and you change the pressure, no change will happen. Okay? Only if pressure can change volume, then your reaction might go forward or backward depending on the delta N. Over here, since delta N is 0, gaseous moles on the right hand side are 2, gaseous moles on the left hand side are 2, no change. Then increase in concentration of O2. Reactants are increased. More reactants, more opportunity to react. It will go towards the product. Yeah, it goes forward, isn't it? Yeah, reaction ho raha hai and suddenly the reactant increases. Oh, let's go towards the products. Simple as that. N2 increases, once again goes forward. Okay, sorry, यहाँ पे decrease लिखा है. N2 decreases. So you are decreasing the reactant. So you are like, oh, I don't have enough reactant. Make more reactant, please. So the reaction over here, what will happen to the reaction? The reaction will go backward, goes back. Similarly, if you increase the anode concentration, if you increase the product's concentration, lots of products formed, the reaction will come back to the reactants. Very logical idea, yes. जो ज़्यादा हो गया उसको कम कर देना है, जो कम हो गया उसको ज़्यादा कर देना है. If something increases, decrease it. If something decreases, increase it. As simple as that. So increase NO2, increases NO, goes back. Presence of catalyst. As we all know, catalyst does not change the reaction conditions at all. In the presence of catalyst, no change will happen. Okay. 2 more cases that we will discuss quickly and our revision is over. Introduce inert gas. Okay, introduce, एक second मैं यहीं पे लिखता हूँ, introduce inert gas at constant volume, at variable volume. At constant volume, my dear friends, at constant volume, if you introduce inert gas, volume is not changing. Since the volume does not change, no change will happen. In the case of variable volume, now what is happening? If you introduce inert gas, volume will increase. Yeah, it's like a balloon. If you put more gas into it, it will increase. So for variable volume, volume increases. This has to go towards, okay, this goes towards more gaseous moles, isn't it? If you increase the volume, the system has to go towards more gaseous moles. But in this particular reaction over here, there is no change. No change for, okay, no change for the given example. As simple as that. Le Chatelier's principle revised. Hardly took us any time. So my dear friends, these were all the ideas that are there in the chemical equilibrium chapter. Very easy ideas, but the weightage of this chapter is important. This chapter finds its weightage almost every year in the examinations. One question comes from it in mains, in advanced. Sometimes it does, sometimes it doesn't. And this chapter forms the basis of the ionic equilibrium chapter. Because ionic equilibrium is just a fancy application of Le Chatelier's principle. Common ion effect, it's Le Chatelier's principle. pH varying in the condition of small acids, big acids, this and that. It's all Le Chatelier's principle applied in a mathematical fashion. Okay, so ionic equilibrium will be discussed in the month of June. Please stay subscribed to the channel in case you don't want to miss that. Alright, and in case this revision was helpful for you, please make sure you hit that like button. We are done revising the chapter of chemical equilibrium in just 30 minutes. And we went into a lot of detail as well, so that's good. So, in case you enjoyed the class, make sure you hit the like button, stay subscribed. And for those of you who are asking questions, kab honge? Questions will happen tomorrow at 8 p.m.